Hello everyone and welcome back to the Cambridge IGCSE 0606 Additional Mathematics course. In this video we will be covering the 12th chapter, which is series. So let's get started. Now the first thing in the chapter is binomial expansion, and this is the formula for it. Now this formula is given in the list of formulas, so you don't need to remember it. But once you start practicing past papers and doing enough questions, the formula becomes repetitive, and you do end up accidentally memorizing it because of how well it may seem complicated at first, but it is actually quite simple. So I'll do this example question for you to just show how you do it. So so x to the power 4, a to the power n, plus then we calculate. So this, I should probably explain this notation. One second. So NR is the same as NCR, which we learned in the permutations and combinations video. So that means the same thing. So if we were to do 4C1, we will find that that is 4 times x cubed times 3. 3 to the power 1 is 3 really. Then 4C2 would be 4 factorial 24 24 to 12, 12, 6. Okay, 6 x squared and then 3 squared, which is 9. Then 4C3 will come back down to 4. Then 3 cubed, which is 27. And then the last term, which is just 3 to the power 4, which is 27 times 3, 81. Okay, so and then obviously you can just sort of simplify this. That gives you x to the power 4 plus 12x cubed plus 54x squared plus 27 into 4, 108x plus 81. That goes a bit off screen, but yeah, so the expansion of x plus 3 whole to the power 4 is this answer right here, and you get this from basically applying the formula, right? So a to the power n is just x to the power 4, then n1 is 4c1 x to the power 4 minus 1 x cubed, and then 3 to the power 1, so 4 into 3, 12, and then you keep applying the formula and you end up with the expansion, obviously until you get b to the power n, which is 3 to the power 4. So a general term in the binomial expansion, this one here, as I've written, is just nr or ncr times a to the power n minus r times b to the r, where r is greater than or equal to 0. So obviously b to the power 0 is the first term, and then n will be greater than or equal to r. So basically n and n must be greater than r in all cases, because say 1c3 is doesn't actually exist, because you can't, because by the definition of combinations you can't choose three different things from one. So now this general term is actually very useful when you want to find some specific term. So let's say if the question asks for a term independent of x in this expansion, well then we're looking for some power of x. So x to the power n minus r is equal to 1 by x to the power of r. Right, so that's basically what we're saying is x to the power n minus r is equal to x to the power minus r. Or quite simply, uh, yeah, that's basically what we're basically looking for, a term in this expansion where x to the power n minus r is equal to x to the power minus r, because 1 by x is the same as x to the power negative 1. Now I won't sorry, I won't recommend trying to use the formula. Just try and list out the only the x terms. Don't evaluate the coefficients. So the first one will be x to the power 10. Then we'll see it's x to the power 9 by x, which is x to the power 8. And then if we continue down, you can see that x is decreasing in by 2 each time. So 10 minus 2, 8. 8 minus 2 will give you 6, 4, 2, and then x to the power 0, which is basically the term independent of x, because anything to the power of 0 is 1. So is this 0, 1, 2, 3, 4, fifth. So we're looking for n, okay, it's 10, 5, um, 2x to the power of 5 to 1 by x to the power of 5. And then you can quite simply see x to the power 5 divided by x to the power 5 is going to end up giving us 1, right? So 10c5, I cannot evaluate this in my head, so I'll use a calculator. 252 to what, 2 to the power 4, 16 into 2, 32 x to the power 5 all over x to the power 5. Let me just check this once more. Yep. And then 252 times 32 gives you 864, and that is our final answer. So just identify the pattern of how the powers of x decrease or increase and find your term. Now, one important thing, I start counting from 0, right? 0, 1, 2, 3, 4, 5 for r, because that is how r starts, n0, then n1. So that's an important thing to remember always, because r is greater than or equal to 0. Okay, now let's move to arithmetic progressions. And these are progressions basically where each term differs from the last term by some common difference or some common number. So if we take an example here, let's say 1, 3, 5, 7, 9, we say that it's the first term is a, which is 1, and then the common difference, which we represent as d, is actually going to be 2, because 1 plus 2, 3, 3 plus 2, 5, 5 plus 2, 7, 7 plus 2, 9, and then so on forever. So d is equal to 2. And then nth term, or u subscript n, is just a plus d n minus 1. So this is a formula, and that basically gives you the term at any position n. So like if I wanted to find the term in the second position, I would write u2, and then we'll use the formula and apply that. So for this one, so a plus d n minus 1 is the same as 1 plus 2 times n minus 1. So this is 1 plus 2n minus 2, which simplifies to 2n minus 1. You can, substitute some n values, check that it actually works, and you'll find out that it's correct. And then if you want to find the sum of any n terms, so let's say I want to find the sum of the first 5 terms or the sum of the first 20 terms or anything, so we can use this formula s n, where n is the number of terms of the sum we want to find. 1 by 2n a plus l, where l is the last term. Now obviously we don't have a quote-unquote last term for a progression that this one goes on forever because there's infinite numbers, but l is basically just going to be un, because that's the technically the last term till we're looking for, right? If I said the first 5 terms, then the 5th term becomes our last term because we're not considering anything after that. So if we were to substitute the definition of L as u to the n, this formula in here, you'll just find a plus a is 2a, and then this one is just copied in here, and outside the bracket remains the same. So that's essentially how it is. Let me just give you an example. Let's say S4 will be, so 4 by 2, 2 into 1 using this progression here, d n minus 1, that is 2 into 2, this is 3, 6, so that gives us 8, and then 16. So if we were actually check, let's say 1 plus 3 plus 5 plus 7 is again 1 plus 3 plus 5 plus 7. If you do this gives you 16. 16 is, well, equal to 16. So that formula also works. You can check this for how many numbers you want. Now the last thing are geometric progressions, which are somewhat similar to arithmetic progressions, but each term differs from the last term by a multiple of a common ratio. So we say the first term is a, and then the common ratio here is r. So you can see that 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, times 2 is 16. So our first term is 1, and then the common ratio with which each of them differ is 2. So the nth term here is a times r raised to n minus 1. So if I were to put this in brackets, so the a isn't affected by the power, only the r is. And this is somewhat similar to compound interest, the formula essentially. So if we, for this progression, we find the nth term, we find that it's actually 2 to the power n all over 2. And you can substitute n values, check it if you want to verify. Now, again, similar, the sum of in terms is represented by this formula, and this only works when r is not equal to 1, because 1 minus 1 gives you a division by 0, which we know doesn't mathematically work. Now, obviously, an r of 1 means that, well, all the terms are the same. So if you were given a question like that, just multiply it by n. It's just 8 times n, just sum. Now, something special about geometric progressions is that some of these geometric progressions converge. So like this progression here, where the common ratio is 1 by 2. Now obviously this will also go on to infinity, but the numbers will keep getting smaller and smaller and smaller. By the time we've reached the 100th term or the 200th term, the numbers will be so insignificant or so small that they actually don't make a difference to any sum or anything at all. So we say that sums like these have a sum to infinity, basically, which is represented by this formula. And then this is the condition for r, if you remember modulus, and then you can expand it. That tells you, so a geometric progression converges when r is greater than -1 and less than 1, and then when it converges, it also has a sum to infinity. So there is also a very nice geometrical representation of this. So if I take a square, let's say, of area 16, right? If we use this one, then if I take another square, actually a bit like this, I would say. This one has, actually, I'll put it down here. That'll be much simpler. This one has an area of 8. Then I take another square here, precisely half of that. That is an area of, actually, I'll take it like this. So if you say this one has an area of 4, because we said this side length is 2, this side length over here is 2. Then if I split this down the middle, 2 and 2, again, because 4 times 4 is 16, then I can find another one. This will be 2. Then like this again, 1, 1 by 2, and so on, so forth. This is going to converge. So well, we know the area of this is 8, so 8 by 2 gives us 4 here, and then we've already found that. So this total length is 2 plus 2 plus 4, which is going to be 8, and then this side length here is going to be 2 plus 2, which is 4. So if we find the area of this whole figure here with this side length and this side, we say 8 into 4, which is equal to 32, right? And let's say if we apply this formula, a is 16, and then 1 minus 1 by 2, 16 by 1 by 2, which is equal to 32. So we find that this is actually one of the ways that this formula was proved, not derived, or it was derived. I'm not entirely sure, but this is the geometrical representation of the whole sum to infinity. As you can see, this remaining area here is obviously made up of multiple infinite numbers that keep getting smaller and smaller and don't really affect the accuracy or the value so much, right? Because eventually you'll end up with some 0 0 0 0 0, some 20 zeros here, and then some number here, which doesn't really affect the value that much. So yeah, that's it for this video. Thank you for watching.